Greetings and salutations, magical chemists. Let's take a closer look at IMFs and their applications. First, we're going to examine London dispersion forces, otherwise known as induced dipole attractions. London dispersion forces and how strong they are for a given particle are determined by what we call the polarizability of a molecule. This is a measure of how much the electron cloud can temporarily shift or move. I kind of think of it as how squishy it is, because if you can squish the electron cloud, you can create temporary dipoles with partial negatives and partial positives that then basically stick to the partial negatives and partial positives of other molecules. Now, these London dispersion forces come from temporary dipoles, but even a temporary dipole can induce or cause a temporary dipole on a neighboring molecule. That's why these are sometimes known as induced dipole attractive forces. But that doesn't roll off the tongue, so I prefer LDFs. The most important thing you need to know about what causes LDFs to be stronger is having more electrons. So if you have a greater electron cloud, aka more electrons, the molecule is going to be more polarizable, more squishy, and the induced dipoles will be stronger, so there will be stronger LDF attractive forces. One of the things you consider when looking for LDFs is molar mass, because if you're comparing two things that have different molar masses, well, an increase in molar mass implies, more electrons, which is the thing we're looking for, which means the molecule is more polarizable and has stronger LDFs. There's another interesting way that you can have stronger LDFs even without increasing the number of electrons. If you increase the surface-to-surface contact area. So for instance, there are two different isomers of pentane. One of them is a big long chain, and the other is a central carbon with little CH3 groups coming off of it. Hopefully, it is clear that the long chain has a greater surface area in between, which honestly gives it a greater surface area for induced dipoles. And if you have greater induced dipoles, you have greater LDFs. The change in surface area can have a pretty significant difference. One of the ways that you can measure strength of IMFs is boiling point, right? A higher boiling point means it took more energy to overcome the IMFs. Well, the boiling point of the pentane in a long chain is 36 degrees Celsius. The boiling point of pentane in like the center carbon style is only 10 degrees Celsius. That's a huge difference in boiling point considering they have the exact same formula. And of course, the same number of electrons. Okay, there is one counterexample about LDFs that I would like to point out because you may or may not remember that LDFs are considered to be the weakest of all of the IMFs. However, there was a caveat. If we said similarly sized particles will have, then LDFs would be weaker, dipole to dipole stronger, hydrogen bonding even stronger. But when you have nonpolar substances that only have London dispersion forces, but they are much larger and thus more polarizable than a small polar molecule, it turns out the London dispersion forces can actually be stronger than the hydrogen bonding forces exhibited by a smaller particle. Crazy but true. And this is heavily AP tested. Of course it is. It's an exception. The good news is you're not expected to know, well, what's the tipping point? How big does something have to be before the LDFs become stronger than somebody else's hydrogen bonds? They will actually tell you. You just have to realize what's happening. So here's a classic example. They say, well, Cl2 has a higher boiling point than HCl. Explain. So notice, they're not making you guess. They are telling you Cl2 has a higher boiling point than HCl. And you're talking boiling point about covalent compounds, you have to talk IMFs. Higher boiling point means stronger IMFs. But wait. If you're trying to determine what IMFs are exhibited by each substance, you have to look at if they're polar or nonpolar. That really is one of the huge determining factors. Well, diatomic chlorine cannot be polar. It has a perfectly evenly distributed electron cloud. But it only has London dispersion forces, right? If you're nonpolar. But HCl, oh my gosh, that's polar. Oops, it is not having fun. Pardon me. Chlorine is very electronegative, but not quite as electronegative as fluorine, oxygen, or nitrogen. Well, it is polar, and so it has dipole-to-dipole attractive forces and London dispersion forces. But it doesn't matter. Cl2 has a higher boiling point. So you have to recognize, oh, it must be because chlorine's so freaking big, right? Chlorine's got a lot of electrons, and there's one chlorine in HCl, but there are two chlorines in Cl2. Lots more electrons, so the London dispersion forces in Cl2 must be stronger than the combination of dipole-to-dipole forces and London dispersion forces in HCl. That's the only thing that could be true. And that's what you have to explain. So let's go ahead and put that in words. Okay, so here's it written down a little more neatly. I have highlighted the most essential thing that has to be noted, and it's the reason that Cl2 has such strong LDS is because it has a large number of electrons compared to H. Well, compared to HCl overall. Luckily, these are not always going to be free response questions. There can also be multiple choice questions and things that are a little more straightforward. So let's go ahead and use our new understanding of London dispersion forces to try these next two problems. You're going to rank the given compound for each one in order of increasing London dispersion forces, aka smallest to largest. So go ahead and try that, and when you're ready to check, unpause the video. All right, increasing LDFs. Well, each one of these is a different molecule. So you want the smallest molecule to the largest, least electrons to the most. And the logic is very similar for the bottom one. For a diatomic molecule, the number of IMFs exhibited will actually determine its state of matter at room temperature. You might remember fluorine and chlorine, the small ones, are both going to be gases at room temperature. But bromine is one of only two liquid elements on the entire periodic table, the other being mercury. So bromine is a liquid because it has a large enough electron cloud. It is thus polarizable enough that the IMS will keep it in a liquid at room temperature. And iodine has such a large and polarizable electron cloud that it is solid at room temperature. So as you can tell, the difference in London dispersion forces based on how many electrons you have can be a very significant effect. Okay, let's move onward and upward and take a closer look at hydrogen bonding, the most poorly named in all of chemistry, because hydrogen bonds are not chemical bonds. Hydrogen bonding we always talk about being fun because it is the attractive force between a hydrogen atom that's bonded to something fun, fluorine, oxygen, or nitrogen, and the unshared electron pair on another atom in a separate molecule of fluorine, oxygen, or nitrogen. We depict the IMFs of hydrogen bonding just like we do other IMFs with a dashed or dotted line, not a just solid line, because then we'd be saying it's a real bond. Hydrogen bonding is honestly part of the reason that life could evolve on Earth. It has it basically gives water very unique properties, including its high boiling point, which you'd be like, what, that just makes it take a long time before I can boil water for pasta. Yes, and it keeps Earth having a bunch of liquid water, which is essential for life. Now let's make sure that you know how to represent hydrogen bonding because it can be sneaky. So now, hydrogen bonding is not a bond. So you are required to draw at least two separate NH3 particles to illustrate it. Let's take a look. Okay, here is an ammonia molecule with covalently bonded hydrogen to nitrogen. Super strong dipole. So along comes another ammonia particle. It's essential to realize that the hydrogen on one of them is going to be hydrogen bonding to the lone pair on the nitrogen on the opposing molecule. I can think of many questions over the years that have shown up on the AP test where they give you a picture like this and ask you to identify which one's the hydrogen bond? It's not the covalent bond. Okay, it turns out hydrogen bonding, just like water, well, it's actually essential to life in different ways. It's essential to life because it's what holds together your two strands of DNA. It's like human body couldn't exist without hydrogen bonding. Life couldn't exist as we know it without hydrogen bonding. It's really exciting. So what's interesting, I'm sure you have learned at some point in biology that cytosine and guanine are like matching base pairs. Adenine and thymine are matching. Well, the reason they match is the number of hydrogen bonds that they can form between them. Oops, I poorly highlighted that. Notice how the dotted line is showing you the hydrogen bonding attractive force. Adenine and thymine only connect with 2 hydrogen bonds, but guanine and cytosine with 3. Now, adenine in RNA will connect with uracil, and hey, uracil is very similar to thymine in that it has basically the ability to form 2 hydrogen bonds with adenine. It is truly remarkable how chemistry and biology are intertwined, if you will. All right, we've talked about this briefly, but now let's expand upon the different basically variables that you could measure in lab that signify the strength of intermolecular forces. So there are 2 of them that are it's funny, they both start with a V and they're both inversely related to IMFs, but they are very different things. One is vapor pressure and one is volatility. Vapor pressure, honestly, is the one that tends to confuse people the most because it's the pressure exerted by a gas, aka a vapor, when it's in equilibrium with its liquid in a sealed container. Wait, there's equilibrium here too? Yup, equilibrium's in everything. So here equilibrium happens so if you have a container of a liquid, like you just leave a cup of water out, eventually it'll evaporate. Some of the molecules of water are always breaking free of those attractive forces and escaping into the air. Well, if you have a sealed container, though they can't escape altogether, they can't fly off into the room, they will eventually be reabsorbed back into the liquid. So there's this equilibrium that happens between the particles that are going from liquid to gas and particles that are going from gas back to liquid. Well, hopefully you can realize that if the molecules are really sticky, aka they have very strong IMFs, then most of them are going to stay stuck together in the liquid. But if you have weaker attractive forces, lower IMFs, well, it's going to be easier and thus more of the molecules will actually be in gas form. So the thing to remember is that when you have lower IMFs, weaker IMFs, that's when your vapor pressure will be high because you're measuring the pressure of the particles of a gas. And there's more gas when there are weak IMFs. Volatility is related, but it's not in a sealed container. This is just how quickly something evaporates. But it has the same relationship with IMFs because, well, if you have weaker attractive forces between your molecules, they're less sticky, they're going to, separate more easily. So that means they're going to evaporate more quickly. So when you have weaker IMFs, less sticky particles, well, they're going to have high volatility. They're very volatile. Isn't that weird? That's totally a word. So things in organic chemistry that evaporate quickly, often nonpolar substances, they are known as volatile solvents. Okay, those happen to be the only 2 things, the only 2 variables, that's the word, that are inversely proportional to IMFs. Basically, if IMFs goes down, these go up. There are a lot of different things that when you measure them, they actually have a direct relationship. So stronger IMFs would lead to a higher measured variable. Let's look at those. We've already talked about boiling point and melting point before. As you can imagine, to force a substance to change state, you are trying to overcome those sticky IMFs. Well, the stickier the IMFs, the more heat energy has to be applied before the molecules separate. So when you have more IMFs, that means that that substance is going to have a higher melting point and a higher boiling point. There is also, interestingly enough, this is related to solubility in water. Solubility, right, is just the amount of a given substance that will dissolve in water. When you have strong interactions between the things that you're dissolving and water, or, a polar solvent, then that means they're most likely to be soluble. That's energetically favorable. So higher IMFs exhibited tends to lead to an increased solubility in water. Those three are by far the most commonly tested direct relationship between IMFs, but there's honestly a couple more. I want to throw these out there just in case you come across them. So surface tension, capillary action, and viscosity. These are all also directly related to IMFs. Well, viscosity, it's basically how quickly something will pour, like honey has a high viscosity and it pours so slowly. Well, that's because honey has very strong and delicious IMFs. Capillary action is how liquid will creep upwards. It'll creep up a paper towel if it's in water, or I believe this is how plants get liquids. I don't know much about plants. And surface tension is why, a belly flop hurts. It's how a liquid will stick together at the surface. Well, all of those things, the stickier or the stronger the IMFs, the higher each of those things are going to be. Just remember the two things that start with a vapor pressure and volatility. Those are the ones that have an inverse relationship with IMF strength. All right, those are all the different variables you need to know that correlate with IMFs. So it would be a great idea to go ahead and practice some of these concepts to make sure they really, stick into your brain. Strong IMFs for all. Thank you for playing with the glories of chemistry.